So I'm just clicking record so that, yeah, that's recording. So this will be recorded and we will put this on Blackboard so that you can catch up and look at it again. So I hope you've had a good week. Welcome back to Maths. So Dr. Abdul, he's uploaded all of his videos now for the whole of the first 4 weeks of his material. So each Tuesday we're going to look at the topics and the questions for this week. So you've got time to, in advance of the session, to have a look at your material on Blackboard. And I will start adding my material shortly so that that keeps up as well. Okay, so this session is going to be followed again by the problem sessions with the teaching assistants, and we'll work through the questions in this week's folder on Blackboard. Okay, so this week Dr. Abdul put his videos on, and the topics we were looking at were the series, the Taylor series, the Maclaurin series, which is to do with linearizing or simplifying functions, turning them into polynomials, so that we can do useful stuff with them. And then he started looking at some numerical techniques for finding roots of equations. So that's finding out when a function equals 0, and he did that using the Newton-Raphson method. And then he had another video which was starting to look at how to do some of these things using Excel. Okay. So I've prepared 2 examples to look through. So these are just going to cover the same things that were in the videos, but slightly different examples. They're simple ones, and that will prepare us to go into the problem session. And what I'm going to do is do them both. I'll do them on paper quickly, and then I'll try and talk you through them in Excel. So part of this module is to get you experienced in using Excel and starting to understand how you can translate the theory of the maths that we're doing to put it into practice. Throughout your course, you're going to use Excel for all sorts of things, for project work, design projects, for analyzing experimental data from labs. And so the more familiar you get with how to use it, and in particular, the more familiar you start to get with some of the functions that are within it that enable you to essentially do simple bits of programming to work things out, the better. I appreciate that some of you might not have used Excel before, and some of you might have used it a lot. So we're just going to try and start at the beginning and just talk you through how to do some basic stuff in it. So not sure if the level will be right for you, but hopefully it will start to get everyone to the right place. Okay. So I've got my eye on the chat as well whilst we're going along. Someone asked a question about the diagnostic exercise follow-up, and so looking at Dr. Steele's info on Blackboard, it says that the assessment will become available on Monday the 26th of October, which is Monday next week, and then it will be there for 2 weeks for you to do that. There are some practice questions which are already available as well, and they'll stay visible until the Friday the 6th of November as well. Okay, so I'm going to try to share my screen to show you a visualizer. Screen 1, share. So I'm hoping that you can see a visualizer, you can see my hand, and we're just going to talk a little bit about Taylor series and illustrate how to do it, and then we'll talk about why we do it in with an Excel example. Okay, so here we go. Taylor series. So there we go. So now that I've shared my screen, it hides the chat from me. So I'll open that again, just in case anything comes up. So the Taylor series, we've got a definition of it, and this is all to do with how to treat functions. So in particular, if you've got functions that are difficult to use, we've got this neat thing, the Taylor series, which means we can convert one function into another function, which will be approximate to our original function in a particular region. So the definition that you'll have seen, the Taylor series of a function of x is equal to f a, the derivative of the function at a, x minus a, and we have this series, so this goes on forever with different powers of the derivatives and the x minus a terms. And the point about this is that it's only an approximation, and it's only a good approximation in a very small region, typically in a local region, and that's the region around A. So the point of the Taylor series is that we want to approximate our function, but we know roughly where we need to be doing it. We don't need to worry about the whole of the range of possible x values. We're going to look at a particular local region, and which is centered on A, and then we can develop the approximation around that. Now, the more terms we add, the better the approximation will become. So both the error will decrease, and correspondingly, the width of the region where it's a reasonable approximation will also get wider. There was a question on the Blackboard discussion board about how do we pick A, and when do we, or how do we decide that A is equal to 0? Okay, well, A could be anything. A is the point in the x range that we're interested in. That's telling us the region. So there are particular instances where we're only concerned with the case where A is equal to 0. So that means that we are just at the point on the x-axis of 0. So we're looking at that particular region. So that's a special case. And when you have that special case, then this, you substitute in A, and that's when we call it the Maclaurin series. So that's when we get that. Okay, so that's the basics of what it is. And you see this is a common subject that comes up in exams frequently. And we want you to have a basic grasp of how to implement it, how to use it, and to know when you might want to use it. Okay, so we're going to look at first example, where we're going to take a case simply the case where f of x is equal to cos x, just to quickly talk through how you implement this. This is an easy one to find the derivatives of. So we can work through the first few terms. Like so. And then we can input those into our Taylor series. So our approximation for cos x will start with cos A minus sine A multiplied by x minus A, and it'd be minus cos A divided by 2 x minus A squared, and then we'll add in this last term, sine x. This time it's over 3 factorial, so 3 times 2 times 1, which is equal to 6, so we can put that straight in, x minus A cubed. Okay, simple. So that's how it works. And of course, then if you're interested in the Maclaurin series, you'd just put in A equals 0, and we would get that. So that's a simple example. I think you're familiar with that and comfortable with that. And what I want to do now is to try and illustrate in Excel how we will do that. Okay, so here's Excel, which hopefully you can see on the same screen. And I've made the zoom quite high so you can see the cells. I'm not sure how clear the equations will be in the equation editor bar here, but you can see the equations as I type them in, so hopefully this will work out fairly clearly. So we just want to explore this function using Excel and just to see how we do a few things in Excel along the way. And we want to see how good is the approximation. That would be a nice thing to look at, how it changes with the number of terms in the Taylor series. So first of all, we just want to see how to plot the original function. So we need to have columns of x, and we want to have a column for our function. Let's call it fx equals cos x, like that. Now, I'm just going to say a few things about Excel as I go along, just to make sure that you know, in case you don't know. Now, Excel treats a cell as normally one of two different things. It's treating it either as a text value or as a number. And when you write text into a cell like this, x or f of x, it's treating this as some text. It doesn't think it's a number or an equation. It just thinks it's some text, and it will just display it as text. And that's as opposed to if I take a cell and put in a number, say 5, it thinks that's a number. So it's making a difference between them. You can tell sometimes which it's thinking because text by default gets lined up on the left, and numbers by default get lined up on the right. So it has two basic things that you want it that it wants to understand. Okay, so our x values, where shall we go? Well, let's go from minus pi to pi, something like that. So the default for Excel is it's working in radians. So if you want to work in degrees in Excel, you'd have to change something or do a conversion. So we want this to be a number, and we want it to be pi. So to put in something that's a number, you can either type the number in. So for example, we could put in an approximate value of minus 3.14. It's going to treat that as a number, but we want to put in pi. So to actually put in an equation or a symbol, we need to start off by putting the equal sign. The equal sign tells Excel that it's going to be an equation coming next. And then within Excel, there are lots and lots of different functions you can use that do useful things. And so the first one is it has stored a value for pi. So we put in pi, I put in minus pi. Now pi is a function, and so every function in Excel is a name followed by some brackets. And then the brackets contain different arguments which the function will process. In this case, pi is a constant, so it doesn't have any arguments. It's the constant value, and we write it in like that, and that will give us minus pi. Okay, now we want to then increment our value of x as we progress along the x-axis. So let's do that. How shall we do it? Let's have a delta x value. So let's say we're going to increase it each time by some amount pi divided by 5, let's say. So that's going to be our increment. So then each time we go to a new row, we're going to increment our value of x. So we take the value before. So you start an equation, you click on a different cell, and then that will input that location into your equation. So that cell is called A2. So it's equal to A2 plus our increment E1. Now we want to be able to copy this cell and to copy it down the column. When you copy a cell, the values of these references will change. So in this case, we want E1 to stay fixed because that cell is not going to be moving. And so there's a special way of doing that with an Excel. You tap on your reference, and you can either do it manually or you can tap F4, a shortcut key. You tap F4, it will put a $sign before the E and a $sign before the 1. That fixes these two values. It fixes the row 1 and it fixes the column E. So that won't change now. If we copy that cell and put it somewhere else, that will be fixed to E1. So now we want to extend that down. to get multiple points on the x-axis. Well, now we can just drag it and it will copy that value. So after we've copied it, now you see, well, it's still the value above. So this reference has changed. A3 has changed because the cell reference is relative to the cell that we've copied it to, whereas E1 has stayed fixed because we fixed that using the dollar signs. Okay, so we can then just drag that down and you'll see that we can get a nice range of values for x. Now we want to input our function, and same sort of thing. So we put in an equation. We want a cos function. So many of the functions in Excel are intuitive, and cos indeed is cos. And as you type it in, it happily gives you a list of functions that are applicable as you're going along. So you can type it in and it comes up there. Yes, that's a function. And often it then tells you something about the arguments it needs as well. So there we are. So as we write it in, we open the brackets, and Excel is also telling us the arguments that this function needs. So if cos needs one argument, it needs to know what's the value of x that we're applying it to. So we're applying it to this value of x, the one next to it, close the bracket, press enter, and it gives us our value for cos of x. Again, we can copy that. You can copy in different ways. You could do Control C. So I've just done Control C. You see the cell now has a dotted line around it. I can then click a new cell and do Control V, and it's copied that cell. It's copied the cell, and the argument has moved with the copied cell to A3. It's the one left of it. The other way of copying that's easy is to drag the corner. You see the little square in that corner? You can click on that, drag it down, and then that will copy that cell all the way down to the bottom. So we've done that. That's great. We've got the data for x and f of x, and now we want to just look at it. And just keeping on the chat as I'm going along. Would we be tested on how to do this in Excel, or is this a demonstration? This is a demonstration. Your coursework that we set you, which is worth 30%, is likely to to use Excel. So we would expect you to develop these skills and to be able to do your coursework using Excel. And the exam after Christmas, we probably won't be asking you to use Excel in that. So we want to do a plot. So to do a plot, you can select the columns that you want to plot. And if you include the column headers, it will use those for naming that. And we go to Insert on the top menu. That brings up a ribbon. And you can see different types of graph that we can insert. We can see one here that looks like a scatter plot. So if you click on that, it gives you a few options for a scatter plot. And we'll pick this one. This plots the points and then puts a linear interpolation line in between them. And it's given us a title based on the column there. So it's worked out for itself that the first row is the title of the parameter. Okay. There we go. And now we want to look at our approximation to this. So to do the approximation, we're going to need to decide what point are we going to approximate around. So let's pick a point. Let's call it A is 1. And now we can do the approximation. Now I've just grabbed those. I'm going to move them to put them somewhere more convenient. As you move the cell, all the references follow it. So now the cell's down here, but none of these changed because the reference within these cells will have stayed the same with those. Okay, so Taylor, let's work through the terms. So for the first term, it was just cos A. That's our value of A there. So we put it in, press F4, and it's fixed. So the first term looks like that. Now if we do the Taylor series with 2 terms, the first 2 terms, then that will be equal to cos A minus sine A multiplied. So the multiplication is the little asterisk key. It's multiplied by our value for x, which is that one, A2 minus A. So that gives us our next approximation. And then we can carry on like this. Someone's just asked, why does A equals 1? A doesn't need to be equal to 1. What we're saying is we want to approximate our function in the vicinity of 1. So A is equal to the value that we're trying to approximate nearby. So we're going to see in a moment when I plot these that our approximation is going to be quite, or relatively good near 1, but not so good further away. So to speed this up, I'm just going to go into the equation bar at the top and do Control C, escape, and then I can do Control V. So I've just copied that equation across, and now I can add the next term as well. Divided by 2, and I'll just put that in brackets as well to avoid any misunderstanding about what we mean. And then we've got x minus a, so x minus a squared. And then with our fourth term, we're going to add sine divided by 6 multiplied by x minus a to the power 3. Okay, so we've had a go doing that. So how do these look? So when you click on the graph, it brings up the data that the graph has been compiled from. And if I just drag that across one, it will add that as a new data set within the graph. And I can do it again. So with just one term, obviously, we've just got an approximation, which is a constant value. And you can see that, well, at x equals 1, the value of a that we picked, then the approximation is good. But far away from that, it's terrible because it's just a constant. Let's add the next term. Okay, here we go. So now you can see we've got the gradient of our function at that point. For a equals 1, that's approximating in this vicinity of x equals 1. Add the next term, a better approximation. Add the fourth term, we get a new approximation. So I'm just going to delete the terms with the lower order Taylor series. Okay, so that's our function cos x going up and down, and then this is our approximation. So you can see in the vicinity of x equals 1, it's a good approximation, it looks like. In fact, it's a good approximation for most of that period from 0 to pi. You can see beyond that, it starts to become a very bad approximation. But if you know the region that you need to approximate within, then this does the job. Of course, we can change the value of a. So if we wanted a different region, say 0.5, we could put that in, and then we'll get the approximation centered on a different region, or we could put in a different value of minus 1.5, and we'll get the approximation now in the vicinity of minus 1.5. So this technique gets a good approximation for a local region. It's limited by the fact it's for a local region, but we can easily decide which region that's going to be. Okay, that's the first exercise that I wanted to look at with you. So I'll go back to the visualizer. There we go. And then the second topic that you were looking at was the Newton-Raphson method. So this was about how to find roots of an equation using the Newton-Raphson iteration. And the iteration that Dr. Abdul showed you shows that you can try to find a root if you have a starting value of x. You can say, well, the next value of x is going to be equal to the starting value minus the function of xn divided by the derivative of the function at xn. And he did a graphical illustration of why that should work. And it works nicely sometimes. Of course, there are other ways to find roots of equations. There are other iterative methods. So the point being here is that there are many instances where you can't have an analytical solution. So that means there isn't a way of manipulating the equations to get a perfect answer for what the roots are. And then you need to use some sort of numerical algorithm to try and identify the roots. And this is just about the simplest numerical algorithm we could use. And then you'll find that there are other more complicated ones as well. So if we were doing this for a problem where f of x is equal to something simple like this, x cubed minus x plus 1, we want to find the roots of that equation. So that means that's equal to 0. And so we're going to need to know f dash of x. Differentiate x cubed, we get 3x squared minus 1. And with those bits of information, again, we can implement this. So we can do that on paper and with a calculator for the simple case, but you'll find that with more realistic cases, which might require lots of iterations or more complicated situations, doing it using a computer is going to help, and Excel is a simple way of starting that. Or you could write a program, a little scheme in MATLAB, for example, which is also a simple way you might try to do this. Okay, so now we want to set up an iteration on this worksheet to work through this. So how are we going to do that? So it's an iteration, so we're going to have n, that's the sort of term of the iteration, which will start at 0. And then we're going to have our value of xn, so I'm going to do x underscore n. That's going to tell you our value of xn. What do we need to know? We need to know the function at that value. And we're also needing to know the derivative of the function at that value. We just worked those things out. So the function is going to be equal to that value cubed. So to do a power in Excel, we use this little hat symbol, and that raises our value to the power 3 minus x plus 1. So when the cell's empty, it treats it as 0. Likewise, we can do this 3 times, so x is b3 to the power 2 minus 1, and that's giving us those terms. But we do need to pick a value for what our starting point for the iteration is going to be. Okay, so let's pick a value, say 1. Okay, so we've got so far, that's good, but now we need to input the next line, and it's the next line that's going to drive the iteration. So n will increment by 1, so n will be equal to the previous value of n plus 1. And now a new value of xn, so this is now x1, that's going to be equal to the previous value of xn, that one, x0 in that case, minus, sorry, I've just made a mistake. Stop that. So that's going to be equal to our previous value of x, which is that cell, x0, and that's going to be equal to minus the function divided by the derivative of the function. And that will drive the iteration to give our next value of xn. And then we can copy these two cells down to find the new values of f and f dashed. Now that we've got that row set up, we can just copy that down, and very quickly we can find the values. So how does that look? Is that converging? Well, it's not converged yet. If we look at a value of x, not sure that's so good. Somebody's asked the question, how do you know if your initial value is too far away from the root? Well, absolutely. It doesn't always work, this method, and it certainly works best if you can start near the root of the equation. So it doesn't seem to have worked particularly well here. We could try just carrying on with the iteration to see if it gets better. And I'm not sure that has got better. Or we can try to find approximately where the root is and see how that looks. So to do that, we can just do a quick plot of the function. Let's start somewhere, say minus 10. We'll put our increment of x up here, so we'll call that 1 for now. So we'll add that increment each time. F of x is equal to x to the power 3 minus x plus 1. So that should work now, get some values. Okay, so we can see our f of x, and we can see that, okay, it has passed through one somewhere around here. So, okay, that's good. So we can plot that and have a look what it looks like. Okay, so we can see well, it's cubic, so you might expect it to go up and then down again. There could be 3 roots to this equation. We can't see too clearly here. We need to zoom in a bit more. So we want to be closer to 0. So minus 10 is too far away. So let's start it closer to the origin. So let's start at minus 2, and then we can decrease our increment size to get a better resolution. There we go. That's nicer. If we make it a bit bigger, we'll be able to see the other side of 0. There we go. So now we can see, okay, it's cubic, so it does go up and down and up again, but it looks like there's only 1 root. So we know the form of the equation would look like that, but this one only has 1 root, and indeed that root looks like it is about minus 1 point something. So we started with 1. That was a bit of a guess, and you can see that's over here. So it took a bit of work for the iteration to actually work its way over to where the root actually is. So we did our iteration, and you can see that our value went up and down, oscillated for a while until it has iterated to the solution. But by taking a look at the function, we can make a better first guess. So if we'd guessed that the initial value is minus 1, which is closer to where the root is, we can then see within 3 or 4 iterations, we're very close to the root. The error becomes negligible. Okay, so you can see that with a function, you have to have a think about where the roots might be. How many roots will there be? And obviously the starting point will affect which root you find. So if there's more than one root to the equation, the starting point will determine which root you find. There might be other roots that you're not finding. So there are limitations to the numerical methods, but sometimes it's the best we have. And by using a degree of common sense and considering the nature of the function and these methods, you can pinpoint where the roots are likely to be, and then you can go about finding them. Okay, thank you. Those are the points that I wanted to cover. That was to illustrate the basic topics that Dr. Abdul introduced to you, and then to show how we can put these into Excel. And I'm hoping that you can see that you can illustrate these things very quickly in Excel. We expect you to be able to do it with pen and paper. So in an exam, for instance, we would normally ask you to do an iterative problem like this by doing it a number of times. Obviously, an iteration can go on for a long time. So in an exam, we would normally say, do the iteration 3 times or 4 times to give you some sense of how long you should do it for. But once it's in Excel, obviously, it becomes very easy to extend that. Okay, looking at the chat, I think that we have covered these topics. Somebody said, are we provided with a formula sheet which includes the Taylor formula and different Maclaurin expansions? Okay, so this year is different from all previous years. So I'll just tell you what happens normally, first of all. In your exams, in all of your exams, there's a university tables and formula handout that you have access to, which has basic mathematical expressions on. There's a copy of that on the Blackboard page, so I recommend you have a look at that. You find it and take a look at it to become familiar with what's included on it, and it would include things like basic Maclaurin expansions. I can't remember exactly what it has on there. So it will have some things like that on it. And that's there for you to use. And then in normal times, with each exam that you do, we also provide any additional equations which are specific to that topic. So you'll get extra equations that are relevant to what you're doing. So for example, in last year's maths exam, I included some extra information, a sheet with various equations for combinations and permutations. And for all the different modules you do, you'll find in past exam papers different examples of extra equations that have been included. So generally, you can look at past exam papers to get a good idea of what will be there. And as an examiner, when we set an exam, we make sure that we have either decided we're testing you on your knowledge of an equation that you need to be able to come up with yourself. Otherwise, we'll make it available to you. But we would expect you to be able to do these derivations. Would expect you to know the definition of a Taylor series and to be able to implement it to find the Taylor expansion, Maclaurin expansion for common functions. Somebody says, what is the point of learning these equations when they can be done on a computer much quicker and easier? Well, if you don't know what the equations are and what they're doing, you won't know how to correctly implement them on a computer. So what we're trying to do here is to give you an introduction to how you connect the theory that you can learn about maths and other topics, how you can connect that to the real world ways in which you would actually implement it. Now, in real life, there's a great deal of stuff that you can do by finding solutions, by just Googling it, or by using a simulator or using Excel, doing something in there. Built-in functions all the time are making our lives easier and faster. But as an engineer, we're concerned with making sure that we take responsibility for the predictions and the models and the recommendations that we give. And that means taking responsibility for understanding what the assumptions are behind it and understanding what the accuracy is, and making sure that there aren't any mistakes that have found their way through. So this is an instance where we are demonstrating how you can combine both your theoretical understanding of what's happening and then see how you can implement it more quickly. In the future, you're likely to do this straight in Excel, and there are many functions that you can use in Excel to do things faster. But what we want you to do is to understand that. So for instance, something I've not looked at today was the solver function in Excel. But for example, if I was trying to solve this equation, so if I take one of these examples and I just highlight it, we're looking at this one. Okay, we want to find the solution to the equation. We want our function of x to be equal to 0 by finding a value of x. So we can do that in Excel, and you can do it by going to Data, by going to Solver, which I've already added in. And this brings up a little package which can do things like this. So the objective, that's this function. Let's clear that cell. Our objective is C3, and we want that to be a value of 0. And we want to make it a value of 0 by changing a value of x. Okay, so we've done it. And Solver is likely to give you a solution to this. That's great, but how do you know it's a valid solution? You're putting your trust into a piece of software which you don't understand. So what we're trying to do is to give you the starting point for understanding where this might be coming from, how it's working. And so in particular, in this instance, you'll see in this cell here, select a solving method. Look at that, you've got 3 different choices there for which one you should use. Which one should use? How do you make that decision? Which one's going to be fastest? Which one's going to be most accurate? Well, that's where understanding the theory, understanding what these methods are, that's where that comes to play. You can pick one of them, you can click solve. Excel's having a think, and it says Solver could not find a feasible solution. Oh no, what are you going to do? So Solver didn't work on this occasion, despite the many billions of pounds that Microsoft have to throw at this problem. It didn't work. So the black box doesn't always work, in which case you have to think about what you're doing. So I'll cancel that one. So the solver will work, but again, you have to give it a better starting point, or you might need to use a different algorithm to find the solution. So that's some reasons why it's worth understanding what's behind the methods. Okay, so now we're going to break out into the separate rooms, and I need, before you go, don't go yet. One of our demonstrators is not able to be with us today. So I'm going to cover his group. So if you were in the group with Noah last week, then I will look after your group today. So I'm just going to copy a link to a Zoom meeting for the group who were with Noah yesterday. So I'm copying that link, I'm putting it into the chat. So everyone else, go to the groups you were in last week. And if you were in Noah's group last week, then join me in the group that I've just provided a link to. Okay, thank you very much, and we'll see you in your groups momentarily. So I'm just waiting for everyone to find their groups before I leave. I can't open the Zoom meeting for my group until I close this one. I can't find my group. Where do I look? That's on Blackboard. What I'm going to do is just copy the different meeting details. So if you remember the teaching assistant that you had last week, you can find your group from that. Or if you're stuck, then you could just join any group and we'll cope with that for today. Okay, I don't see any more questions, so I'm going to leave this one now and then meet up with my group separately.